Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Okay. Hi everybody, welcome to today's colloquium. It's a great pleasure to introduce Scott Kuindersma. He got his PhD from UMass Amherst, where he worked with Rod Gruppen and Andy Bartow. Then the last 2.5 years, he's been working with Russ Tedrake at MIT. His research is broadly in lag locomotion with a focus on optimal control and machine learning. And in the past, he's already worked with some really amazing robots. I'm sure we'll see some cool videos later on. He's worked, for example, with the U-Bot at UMass, the NASA Robonaut 2, which is one of the robots that's actually deployed in the space station, right? And over the last 2.5 years, he spent, I think, maybe even more time than he wanted on the DARPA Robotics Challenge with the Atlas robot, where he's the lead of the planning and control part. So looking forward to your talk.
Okay, thank you very much, Dieter. Hey everyone, I'm really happy to be here today. So I'm going to talk about some of the work that I've done designing optimization algorithms to control complex physical robots. But I'd like to start with just a little bit of a reflection about the recent history in our field. So a lot of people are calling this past year the Year of Robotics, okay? And there's at least a couple reasons for that. The first is we've seen this huge increase in interest from technological giants like Google and Amazon and science funding agencies around the world. And they're investing millions of dollars and snatching up all of our best PhD students. And the reason for this is they anticipate that with small extensions to the state-of-the-art and many of these systems, they can start to have a real impact on both the private and public sectors. The other reason why people might call this the Year of Robotics is we've seen some of the most amazing examples of robot hardware in history. Okay? So these are just a few of the robots that come to my mind, but there could be other ones that you could imagine adding here as well. These robots are physically capable of doing amazing things. Okay? Walking over challenging terrain, carrying heavy loads, precisely and delicately manipulating objects. But it's still not commonplace to see them doing any of these things. And the reason is that their physical complexity challenges our best computational tools for controlling and analyzing them. And so we're now in this situation where computer scientists have the opportunity to raise the capabilities of these systems, to change the way that they move through the world, and to allow them to do many of the things we know they're able to do in principle. And the stakes are incredibly high. As all of you know, in 2011, a tsunami impacted the Fukushima Daiichi nuclear power plant, which eventually led to a triple meltdown. And in response to this, some of the best robotics agencies around the world sent their field robot technology to help workers try to recover from this event. But by and large, this environment proved far too challenging for even our best field robots of the day. And it's the case now as it was then that the best option for people who are trying to mitigate the effects of this disaster is to send human beings into this dangerous environment to do basic inspection tasks. And in the past year alone, 2 workers have died due to accidents while trying to perform some of these tasks. This is just one example, right? We can also imagine systems that we can drop into remote locations that can run for hours on end and dispatch aid or medicine to remote populations. We can imagine planetary exploring robots that can explore much higher percentages of surfaces of planets and asteroids into caves and craters and up steep slopes. So the structure of my talk today is as follows. In the first and main part, I'm going to discuss some of the work that I've done using convex optimization to control Atlas, which is one of the robots you saw on that first slide. In the second part, I'm going to more briefly talk about variable risk control algorithms that I've used to do risk-sensitive control on physical systems. And finally, I'm going to end with a brief overview of the types of problems I'm interested in tackling in future work. Okay, so as Dieter mentioned, since 2012, I've been the planning and control lead for MIT's DARPA Robotics Challenge team. So for those of you who are unfamiliar with this program, it's basically directly inspired by this Fukushima event. And so the idea is that teams participating will either build, or in our case, win robots, which we then program to raise their capabilities in the context of disaster response tasks. Okay? So as our sort of trajectory through this program has been to compete in a simulation phase where we did a variety of tasks. I'll show you a couple of videos from that later on. And we eventually won this robot from Boston Dynamics. It's called Atlas. And so we're doing things like writing control code and state estimation and perception and all these good things to make it a functional and practical system. So just to give you a few sort of parameters of this robot, it's really large. So I would say it's sort of NFL scale, right? It's 360 pounds or 340 pounds, 6'2". It's hydraulic. It's got 28 hydraulic actuators and an onboard electric hydraulic pump. It's got a variety of handy sensors, including a Hokuyo LiDAR, stereo cameras, really nice KVH IMU for doing state estimation, force torque sensors, and so on. If I had to pick a couple adjectives to describe this robot, I'd say it's strong and it's reliable. If I had to pick a couple more adjectives, I'd say it's noisy and it's messy. But as a controls person, from a sort of practical point of view, these two are probably the most important. So in the competition, we've already done some kind of cool things with this robot. So in 2013, in December, 16 teams from all around the world descended on a NASCAR racetrack, okay, and took over the pit crew garages, filled them up with computers and robots, and hacked away for a week and got our robots to do some pretty cool things, which included, for example, turning industrial valves. Notice the Hollywood-esque apparatus that DARPA has put together for us here. It's pretty cool. Grab fire hoses and attach them to spigots, manipulate power tools to cut through walls, clear debris out of corridors, open doors and walk through them, climb ladders, walk over cinder block terrain, and even slightly ridiculously take an Atlas, cram it into the passenger seat of a Polaris Ranger, and have it drive down a winding course. Now, all this is happening through sort of a remote communication with some human operators that are sitting on the other side of a degraded and delayed network link. And so the idea was that this was meant to discourage direct teleoperation. So we had to think very carefully about how we specified intentions and goals to the robot, for example, in terms of the objects we can perceive and their internal degrees of freedom. And then we relied on motion planning algorithms that we developed to handle all the details on the other end. So in terms of motion planning, we had some pretty cool techniques. For example, we could do whole body kinematic motion planning in real time by solving sparse nonlinear optimization problems in the background. So here's an example of a person dragging the robot's end effector to different poses, and the planner is responding basically instantaneously with feasible whole body configurations. On the locomotion side of things, we had some nice techniques for segmenting terrain in front of the robot into a set of convex safe regions, and then planning sequences of feasible footsteps through those regions. This is work that was led by a grad student, Robin Dietz. So what I'd like to talk about is my particular contribution to this effort, which was to take task-level inputs, like desired footsteps or desired manipulation actions, and turn those into a robot that is stably executing those things in the real world. Let me first try to convince you that that's a hard problem, okay? So we know a few things about humanoid robots. We know they're rigid body systems, so we know how to write down the nonlinear dynamics for systems like this using a manipulator equation, of course. Humanoids also have this property that they tend to be high dimensional. So in Atlas's case, it has a 68-dimensional state, where the state vector is just the positions and velocities of all of its degrees of freedom, and it has a 28-dimensional input, which you usually think about as joint torques. What's more, it's not just this high-dimensional nonlinear system. It's also, as a walking system, is constantly making and breaking contact with its environment. And every time contact is made or broken, we enter into a different dynamic mode. And these transitions are accompanied with impacts, which cause discontinuities in our velocities and thereby break gradients in our optimization algorithms and so on. So solving, for example, trajectory optimization problems for high-dimensional nonlinear hybrid systems constitutes a significant computational challenge. That's not to say it's totally impossible. So there's been a lot of great work in this area, including work from Oscar von Sturck and his students, where they've used direct collocation methods to design trajectories for a small humanoid robot. Katya Mumbar has done nice work with multiple shooting techniques to design open-loop, self-stable running motions for a planar simulated humanoid model. I guess I don't have to tell this audience about the great work that Emo and his students are doing here, actually doing MPC, or model predictive control, for high-dimensional systems like this by exploiting certain smoothness assumptions in the contact model and thereby recovering gradients. But I think the short story is, if you want to take the most complete description, dynamical description of the system and try to use our best tools from optimal control to solve it, you're looking at runtimes of, say, tens of minutes to solve these problems. Now, that wouldn't make for a very responsive system, right? So if I told it to walk from point A to point B and it has to sit there and think for tens of minutes, that's not super useful. Now, there's an obvious counterexample to this, right? In robots like Asimo, for example, which are not, they can go onto a talk show and they can walk around in all these different patterns, and they're not sitting there thinking about what step to take next. So what's going on here? What's going on is that the brilliant engineers that have designed the system and systems like it are exploiting key physical insights of the problem to simplify computation. So you might have heard of ideas like zero moment point and so on. I'll explain exactly how you get to that in a few slides. And in many cases, the physical bodies of these robots are designed in some way to coincide with these assumptions. They'll often have big flat feet, and they'll have sometimes their center of mass will coincide very closely with the origin of their pelvis or torso, so you don't have to worry about computing center of mass and Jacobians and things like that online. But so far, there's been this sort of gap between these insight-based or heuristic-based control techniques and our best tools from numerical optimization and control. And so what I'd like to propose is a way that we can sort of put these things together in a fairly general framework, which might look something like this. So here we have Atlas with all of its complexities. We're going to design some physical mapping that's going to lead to reduced dynamics. Okay? I'll talk about a few different ways you can do that in a couple slides. Once we have this physical mapping, we have a reduced dynamical system on which we can then design trajectories. And given these trajectories, we can stabilize them using our favorite techniques from optimal control. The output of this process is then going to be an optimal cost-to-go function or a value function for this reduced system along this trajectory. And then the idea is that we take this cost-to-go function and we use it to construct a convex optimization problem that is going to try to descend this cost-to-go while reasoning about the instantaneous dynamic, contact, and input constraints for the full robot. Okay? So you can think about this part on the right as happening offline, and hopefully we make design decisions in our reduction that make the system sufficiently responsive. And then we're going to require that these convex optimization problems be, we should be able to construct them and solve them sufficiently fast to support real-time control in a physical robot. So how do we go about coming up with reduced dynamical models of a system like this? Well, one way to do it is to think of a sort of chain of reasonable physical assumptions, right? So one thing people typically do to start is say, I don't want to worry about torque saturations during the planning process. Okay, so this is not a bad assumption when you have a robot like Atlas with its hydraulic and can generate 700 Newton meters of torque at its ankle. Okay, and what happens then is you already have a significant simplification of the dynamics. So now we're not just writing down dynamical equations in the 34 generalized coordinates. We can just reason about how the net external wrenches acting on the system correspond to rates of change in the linear and angular momentum. So we're kind of writing down the dynamics in the floating base coordinates, if you will. So this idea has been looked at recently in the literature under the name of centroidal dynamics by a couple of people. We can go further and say that if the contacts of the system are sort of locally planar, then we don't have to reason about some set of ground reaction forces. We can just reason about the center of pressure, just sort of a weighted average, and the net ground reaction force acting at that point. If we further say that the angular momentum of the system while doing normal stable walking or standing and doing manipulation tasks is negligibly small, which is often the case, then we can just set that to 0, and what we get back is then the so-called zero moment point or center of pressure dynamics, which is low dimensional. We're just reasoning about this point on the contact surface called the center of pressure, but it's still a nonlinear function of the center of mass state and acceleration. If we make one more assumption that we know something about the center of mass height, that it's follows some nominal trajectory, or that it's a constant, we get back something that's very nice indeed, which is this time-varying linear dynamics, whose state is the center of mass position and velocity, and whose input is the center of mass acceleration. Okay, so this is nice for a couple reasons. One is we have an output, which is the center of pressure, which, given a desired set of footsteps, we can easily design trajectories for, using piecewise polynomials or something like that. And then given these trajectories, we can stabilize them using our favorite techniques from linear control, like time-varying linear quadratic regulators. Okay, so this is a very standard way to do control design for a system like this. There's even a command in MATLAB called LQR. That's how ubiquitous this is, right? But it turns out for this particular choice of dynamics that you can do a lot better. So it turns out we can take that output LQR problem and write it down as a quadratic function, quadratic cost on state in an infinite horizon problem with some additional constraints. And then when we crank through the optimal control solution, which is the differential Riccati equation, we find that the optimal cost to go has a really nice form. Okay, I guess I don't have a mouse. So we have a quadratic matrix here, which is non-time varying, which means that the remaining two terms that we have to solve for are just linear differential equations. Okay, so that's really nice. That means we can design an iterative algorithm to solve these linear differential equations instead of having to, for example, integrate backward using ODE 45 or something like that. So the short story here is that for the most ubiquitous walking model in the literature, that you can solve optimal control problems for even long walking trajectories in tens of milliseconds. Okay? So that's pretty cool, because that means we can, if we want, replan optimal controllers on the fly as we go. So what do we do with this optimal cost to go function once we've computed it using this efficient algorithm? Well, you can always simply derive the optimal controller from it, of course. And in the case of this type of controller, we have the HJB equation, which is the minimization of a convex quadratic. And so this has a closed form, which is a time-varying linear policy. But recall that this U tilde here is the center of mass acceleration in our reduced model. And really, we want the robot to ultimately be doing something with this optimal control solution. And for a system with unilateral contact constraints and torque limits, we shouldn't expect that the system can arbitrarily accelerate its center of mass, right? And in fact, no matter what sort of mapping you choose, whatever the inputs to this reduced mapping are always going to be subject to the physical constraints of the real robot. So really what we want to do is perform this minimization subject to torque limits, friction constraints, and so on. So that's exactly what we do. Unsurprisingly, the resulting thing is a quadratic program. So here we're just minimizing that quadratic from the previous slide, and then subject to the constraints of the robot in its current state. So we can write down friction constraints as linear inequalities by using conservative polyhedral approximations of the friction cone. We can add in torque limits, no problem. And of course, we can write down the actual dynamics of the robot, which are instantaneously linear. And since we're fully in the land of quadratic programs now, we can add in any other constraints that might be useful at a sort of task level, like making sure the feet don't accelerate with respect to the ground if we're relying on them for stability and so on. Okay, so I've talked a little bit about each of these pieces. I'm going to come back and say something about what happens when you make a different model reduction here. And I'm going to tell you how we formulate and solve these problems, these convex optimization problems, really fast. But I'd like to stop here and just show you a couple videos from simulation, so the kind of things we can do with what I've said. So we did a lot of work in simulation as part of winning the Atlas robot to begin with. So here's just a couple videos. This is a video of the robot sort of falling and then walking in our in-house simulator Drake. Okay, and And as part of the VRC, I guess some of the people in the audience here know that you have to spend a lot of time getting things to work in Gazebo, which is a different type of simulator, which has numerous numerical issues associated with it. But eventually you can get your things working. So here's us walking around one of the qualification worlds. And this is using state estimation and terrain estimation and all that good stuff. And so you can see that because we have this sort of whole body variables inside this QP, that we can recruit the arms while walking and things like that. One of the other things we had to do for the VRC was walk through this sort of simulated knee-deep mud, which is kind of fun. So our approach is just to truck on through. And then once you get out of the mud, you have to walk over this rolling gazebo hill terrain. And so we were one of just a couple teams that was actually able to do this entire event on 2 feet, which we were pretty happy about. And anyway, we did well enough to win ourselves the real thing. And I think we might actually have the most expensive unboxing video on YouTube. I'm not totally sure, but it's a good shot anyway. So we get the robot in-house, and we're really excited about trying out a lot of these ideas that we developed in simulation. But quickly, as often happens, you realize there's many hardware challenges that need to be tackled first. So here's just a few of my favorites. But immediately you realize that there's no such thing as, of course, commanding pure torques to a joint that a simulator will happily achieve for you. You have to do a little bit of work to get that abstraction. So Atlas, for example, has significant joint friction in all of its joints. So here's a couple empirical friction curves I gathered. And depending on where you look, you might have some significant hysteresis, or you might have something that looks like a nice Coulomb friction model, or maybe even some Strybeck effects over there. So the point is, though, you have to think carefully about this kind of thing and try to model it in order to get the type of control performance that you want. In addition to this, we actually didn't have direct joint force sensors, which means it's kind of hard to do force control. So what we ended up doing is having to use the pressure inside the actuator chamber as an indicator for the joint torque, but of course it's on the wrong side of all this friction, so it's not quite accurate. So in practice, that meant I spent a lot of time doing things like this, right, and getting the low-level control to work. But eventually you get that going, and then there's a few sort of sensing challenges you have to get over, like there's significant backlash in many of the joints. In addition to that, we don't have any joint encoders on those joints, so we don't really know where the feet are to within a couple centimeters. And surprisingly, the robot actually has mechanical compliance. So if you look at this video, here's an example of the robot walking on flat ground. And its feet are not pitching or rolling in reality, but they are in the state estimate, and that's because the linkages between the actuator and the joint output have flex in them. So we have to put these sort of, we have these model-based corrections that we have to add on top of our state estimator. Okay, but the short story is you do all the low-level work, and then you get your nice abstraction layer, and then you can start to work on your high-level stuff. And basically, we were able to take the things from simulation and directly put them on the robot, which is awesome. But first, you have to make sure that you can formulate and solve those optimizations really fast. If you have a controller that takes tens of milliseconds to compute an input, you're not going to be walking very far at all. So how do we do that? Well, we made an observation about the particular type of quadratic program I described, and in fact, many such quadratic programs that have shown up in the literature recently. The key observation is the active set of inequality constraints change very infrequently between consecutive control steps. Now recall the inequalities here have to do with torque limits, and they have to do with friction, polyhedra, and things like that. So you can intuitively surmise that if you were going up against the edge, the boundary of these constraints, and then back off again very rapidly between control steps, that something probably bad's happening on the robot. It's actually true depending on how you write things down, right? So if you write things down using a standard sort of simulation type of parameterization of polyhedra, then you can get active set changes by just changing the direction of ground reaction force. That's not so good. But of course, you can just fix these sort of things by just using different parameterizations. You can also exploit the fact that we have these low-dimensional models that we're computing optimal control solutions on. Because in the solver that I'm about to describe, we're constantly solving these linear systems associated with the KKT conditions, and we can do that really fast by exploiting this low-dimensional structure that exists in that linear system using things like the matrix inversion lemma. Okay, so how do we solve it really fast? So here's an algorithm. We take the QP, we can always write it in this canonical form, And then because we know that in our case W is positive definite, this is a convex QP, and the KKD conditions are going to give you a necessary and sufficient condition of optimality for a feasible point. Okay, so then we take the active set A from the previous iteration and we just solve that linear system in red. We check to see if the inequalities are satisfied. If they're satisfied, we know we have the optimal solution and we're done. If they're not satisfied, we have some rules about how we change the active set and resolve the linear system until either the optimal solution is found or we hit some maximum number of iterations, at which point we fall back to a more reliable sort of interior point method or something. In practice, that second thing happens very infrequently. So we can do a lot better than sort of all the best off-the-shelf solvers, and here's the reason why. So if you look at the number of solver iterations for typical walking, about 97% of the time we're just solving that linear system, and we have the optimal solution and we're done. Okay, so the active set is changing almost never while walking. So that's pretty useful. We can exploit that. We're also using this to sort of speed up our simulation engine. So we're using sort of LCP-based approaches to simulated rigid body systems. I'm not going to talk about that, but if you're interested in that kind of thing, happy to talk about it offline. Okay, so let me show you some of the things that we can do with the robot after all of this, right? So here's just a couple of the first balancing experiments I've tried. So this was putting the robot in the lab and sticking a pallet jack under its feet and jerking it around back and forth and jacking it up and all this stuff, making sure the robot can balance despite these perturbations. On the bottom, you see it going through a series of more or less random whole body collision-free motions just to make sure that the envelope for stability is sufficiently large for what we need. And already with a balancing controller, we could do some things that we couldn't do before using the sort of nominal balancing mode provided with the robot, like picking up things from the ground. Seems simple enough, but it turns out if you're limited with how low you can crouch, then picking up things is hard. So if you happen to have seen some footage from the DRC trials in 2013, you probably saw most of the Atlas robots had these ridiculous wrist extenders to help them pick things up off the ground. So it turns out we don't need wrist extenders anymore. Incidentally, I call this the loneliest game ever. Okay, so this is the robot localizes the board on the ground, does a motion plan to pick it up, executes the plan, grabs it, and then drops it again and repeats. So the idea is, if the robot can do this 5 times in a row on a Friday, we probably didn't break any of the code that week. This is real time. Yep. All the videos will be real time unless they say so. Okay, so after we can do balancing, we can do walking without too much extra effort, right? So here's an example of just walking in our lab pretty slowly and carrying a truss, right? So I didn't tell the robot there's a truss in its hand, and so this is acting really like a constant perturbation to the walking controller, just to make sure that we're robust enough to do this kind of thing. But in principle, there's no reason to do things this way, right? So we have force sensors in the wrist. We can estimate external forces acting on the robot. We're always changing the constraints of our quadratic program online, so we can add these external forces in, and the robot will directly compensate for any forces that it can acting on its body that it can sense. Here's another thing we couldn't do before. You might have seen videos of Atlas typically walking sort of one step at a time, right? So take 2 feet up onto a cinder block, stop, rescan the environment, and repeat. And the reason for that is that the state estimation drifts significantly over time because we're fusing together IMU information. Even though the IMU is very good, it's not perfect, with leg kinematic information, which is very imperfect on Atlas, all the backlash. So it's really hard to make your state estimate not drift. So this is a collaboration with my colleague Morris Fallon. So what you're seeing here is a highly accurate walking controller in a closed loop with a LiDAR-based state estimator. So this is stuff that was adapted from Nick Roy and the students, actually. So we're registering Atlas to a pre-computed map as we're walking. Yes?
How many steps are you planning in advance?
We plan the entire thing all at once here. We have recent stuff where we're doing receding horizon footstep planning on the robot, but that's not what's happening here. So the point here is that I can just make one plan and just execute it with like centimeter level precision all the way up, which is something we were not close to being able to do before. So we focused a lot on getting the robot to walk accurately as a means of walking faster because, well, if you don't stop every step and rescan the environment, you're going to tend to move through the world faster. Another way to go faster is just to walk faster, right? So on the top, you see the standard sort of BDI stepping behavior that's provided with the robot that many of the teams are still using. Below is our controller as of last November, where we basically just cranked up the speed, and we're able to walk about 8 times faster than the nominal walking. We haven't really been optimizing for speed up until this point, but we think we can do a lot better than this. This is not a terrible start. And one thing that was really cool is the robot sort of disappeared for several months, and it came back about a month ago. And it's 75% different, okay, which is always fun right before the final competition. So from the knees up is basically different actuators. The arms are mounted differently. There's different mass distribution. There's an electric head and all these different things that weren't there before. I was able to get it to walk again in less than an afternoon. So I think that really speaks to the power of the tools that we've been developing in all parts of our system, that we can handle these very large changes with little effort. Okay, so I promised I'd say something about what happens when you make slightly different reduction decisions here. So let's look at the case when we remove 3 of those 4 assumptions I made previously. So now what happens is the planning problem becomes harder. So now we're, instead of doing these simple piecewise polynomial trajectories and doing TVLQR in a low-dimensional system, we then have to solve nonlinear optimization problems, which are easier than solving it with the full dynamics, but still take on the order of a couple minutes to solve. But the upshot is that we can use the same types of optimal control techniques and the same types of online convex optimization to stabilize the resulting trajectories, and we can do relatively more things. So here's an example of stabilized jumping in simulation, okay? And then also jumping down from a height of 2 cinder blocks. So this is too high for Atlas to actually step down onto because of the geometry of its legs. In addition to jumping, we can also do a lot faster locomotion through running. Okay, so this is a stabilized running gait for Atlas. So we're really excited about taking these really highly dynamic motions and putting them onto the robot. But we also view this as a nice way to generate sort of multi-contact plans for example, getting up from the ground after falling, which is a problem we actually have to think about now, and climbing out of a car after driving, which I wish we didn't have to think about. All right, so just to summarize the contributions from this part of the talk, I've talked about this sort of framework for piecing together these model reduction-based techniques along with 2 of our best tools from optimal control and numerical optimization. I've talked about efficient algorithms for solving QPs that arise in control problems and simulation problems. I've talked about how we can solve LQR problems for the most ubiquitous walking model in literature extremely fast. I implemented all these ideas on Atlas, and it's received hundreds of hours of experimentation. It's being experimented with right now, even though I'm not there. I'm sure I have emails to look at it after this talk. And all of the code is open source, right? So you can download Atlas onto your laptop and make them walk around. There's people who are taking this control code, putting on quadrupeds and everything. Okay. All right, so I'd like to talk a little bit more briefly about a sort of different set of ideas that I've worked on as well, and doing sort of variable risk control. And I guess by way of a segue, we can just acknowledge that we won't always have these $2 million robots with missile-grade IMUs in their pelvis, that in general there's going to be uncertainty associated with the systems we want to control and even the outputs of our controllers. So here's a sort of uncertain task. Okay, so this is the U-Bot 5. So this is a little humanoid robot. It's about 20 kilograms, and it's got wheels instead of legs. And here it's trying to lift a laundry detergent container, which is sort of heavy relative to its arm strength. And it actually has liquid inside the bottle, which has a non-negligible dynamic effect on the system. So if you lift things the wrong way, then you can actually have some undesirable effects, right? So this has some interesting properties, right? It has this liquid sloshing around inside of a bottle, and that's not something you can ignore, but it's also something that's very difficult to write down a dynamical model for. So what can we do here? So one approach is to take a sort of machine learning perspective, right? Where we define some space of controllers, which is parameterized by a vector theta. And we can evaluate these controllers on the physical system and receive some noisy signal or performance or cost. And then the idea of these algorithms is to minimize some functional of this noisy signal, like the expected value. So there's been a long history of work in this general type of problem, right? A lot of it's focused around sort of local stochastic gradient descent techniques and so on. And largely people like this sort of thing because it allows you to be sort of model free. Okay, so depending on how I write down this controller space, I can put in as much or as little dynamical model information as I'd like. So another type of algorithm that's suitable for tackling this type of problem is a response surface methods, okay, of which Bayesian optimization is one type. And the idea here is that you model the cost function using a Gaussian process prior. Then we collect data by executing different controllers on the robot, and then we can compute a posterior distribution of cost as a function of the policy parameters. And then you can imagine, given this posterior distribution, that we can globally select the next best policy to try according to various criteria that might balance exploration and exploitation in some principled way, or be greedy if you'd like, or whatever. But I'd like you to consider a cost distribution that looks more like this, okay? So here we have our sort of one-dimensional policy parameters, some cost function, and here the variance of the performance is a function of the policy parameters themselves. I would argue this is the sort of norm in a lot of the physical systems we care about controlling, right? So you can imagine certain policy parameters being sort of close to the edge of stability and things like that. And now if you're able to capture a distribution like this, you can imagine you might not just want to minimize the average performance, maybe you want to be risk averse by minimizing the average performance plus a couple of standard deviations, or even be risk-seeking if you just care about finding maybe the one-time best performance of the system. Now, this idea has quite a long history in control, so it's under the name of risk-sensitive control. So early work from Jacobson and Whittle looked at generalizations of linear quadratic Gaussian techniques to the log exponential cost functions, which have a relationship to those confidence-bound types of things I just showed. There's even been work in policy gradient techniques that is capable of doing this kind of thing, and in generalizations of TD algorithms and so on. But underlying all these approaches is sort of assumption that the sensitivity to risk of the system is really a function of the system itself, right? I would argue that for many of the field robots, for example, that we care about, that the sensitivity to risk is going to be a function of the state of the system, right? So you can imagine like a Mars rover that's operating near the edge of a crater is going to be more sensitive to the variance in its navigation performance versus when it's in the middle of a Martian desert. Now that's a kind of a problem for the machine learning approaches among these, right? Because you can imagine if you're changing your objective function on the fly, that you're going to have to do some sort of physical trials in order to make some progress toward minimizing that new objective. But if we can capture a cost distribution in the way that I've just cartooned for you in the previous slide, then you can imagine running optimizations offline that allow the system to change its risk sensitivity. Okay? So that's the idea. So I did some work in this area where we use more general models than Gaussian process models that are able to capture heteroscedasticity in the cost distribution. And unfortunately, many of these models have the property that the posterior distribution is intractable. Okay? But by extending these to the optimization case, I was able to show that for many of the things we care about, like expected improvement, we can efficiently approximate these values and their gradients to do things like sequential quadratic programming and things like that. I also introduced things that make sense from the risk-sensitive control perspective, like expected risk improvement and things like that. Okay. So let me show you what the learn controller from that previous sort of learning sequence looks like. So that was after 30 trials on the robot in a 7-dimensional policy space. And these are all different executions. So this is extremely reliable. And what's cool is it's actually using the sloshing of the liquid in the bottle as part of its learned solution. Okay, you can see that sloshing sort of canceling out the forward motion in a reliable way. So that's kind of cool. And what's better is that we don't just get one learned policy out, right? We have this learned cost distribution. So I can do things like tell it to show me something that is risk averse with respect to translation, which was one of its cost terms, right? And it comes back with this with no additional learning on the system. You can do the same kind of thing for energy if you'd like. And I've done these kind of things, and you can validate all the results with statistical significance. Here's another risky experiment. So here's the U-bot again, and you might see off to the left is a sort of sneaky punching boxing glove, right? I call this the setup the punchulum for obvious reasons. So here the robot's balancing, minding its own business, and this thing comes and slams into its back and knocks it over. So the task here is to learn reactive arm motions that can help stabilize the robot after unpredicted impacts. So here's the failure again, and then here's the learn controller after about 35 trials, I think. So again, not only do we have a single learned controller, I can also say, show me what you believe to be a low-risk recovery strategy. And it comes back with this, where in this second plane, I color things by cost, where green is good and red is bad, so sort of all uniformly the same color means low variance. I can ask it to show me what it believes to be a high-risk recovery strategy, and it shows me this, which is something that fails about half the time. Okay, so just to summarize the contributions from this brief section, I designed new types of Bayesian optimization algorithms that are capable of dealing with systems that have input-dependent variance. There are sort of global versions of these algorithms, which are direct extensions of Bayesian optimization, and sort of local versions, which are more like actor-critic algorithms, which I didn't talk about. And these algorithms are unique because they're sort of variable risk. It allows you to, on the fly, with no additional learning trials, change the risk sensitivity of the system. Okay, so just to try to wrap things up, I'd like to talk about a few sort of areas that I'm interested in pursuing in future work. So efficient and beautiful legged locomotion is ubiquitous in nature, but it's virtually absent in our mechanical systems. So these are two robots that I consider to be fantastic feats of engineering. Okay? So on the right, we have Asimo. I've already talked about Asimo. On the left is the Cornell Ranger. Okay, so this is built by Andy Ruina's group at Cornell. And so this robot has the world distance record for walking. Okay, so this robot is able to walk over 40 miles on a single battery charge. Okay, it's over 30 hours of continuous walking. That's really impressive. And the reason why it can do that is because there's a cost of transport, it's the energy used divided by the mass times the distance traveled, which is basically the same as a human being. Okay? That's a really impressive achievement. But what you're seeing it do here in this video is basically all it does, right? It walks sort of nominally on flat terrain with some slight side-to-side maneuverability. By contrast, Asimo on the right can do a variety of things, right? It can walk around in more or less arbitrary patterns on the ground, it can climb steps, it can hop on one foot. But you've never seen Asimo run for more than, say, 45 minutes, right? And it's not because Asimo's batteries are just lower quality than the Rangers. On the contrary, it's because the cost of transport of Asimo is 10 to 20 times that of a human being. And even if we factor out inefficiencies in its actuators, and we just look at the mechanical cost of transport, which is a function of the mechanism, the control system, the fact remains. And the reason for this is largely computational. It's because efficiency requires that we think about as much of the complex nonlinear dynamics of the system as possible. And legged systems in particular have underlying mathematics that challenges our best optimization algorithms due to the discontinuities in their normal way of getting around the world. And so I think they're sort of everything you want in a research problem because they have amazing practical impact if you can solve these sort of things. But also the advances algorithmically for this general class of systems is going to have broad impact to things like actuated prosthetic devices, to systems that dynamically interact with their environment for manipulation, or even for systems that are yet to be built that are somehow multimodal, that can perch and run and fly. I've talked about sort of two qualitatively different approaches to control. One where we think very carefully about the system, we do system identification and careful calibration, and then we use the model inside of an optimization algorithm. The other where we put in no model information whatsoever and just rely on sample-efficient stochastic optimization algorithms. I think the best field robots of the future are going to have elements of both of these things. They'll be able to sense and adapt to non-stationaries and their dynamics. They'll be able to estimate uncertainties in their physical parameters and feed that back into robust control design algorithms. I think there's a tendency to build ever more precisely calibrated, ever more well-tuned robot systems, but I think the reality, for example, of planetary exploring robots is that they will be modular, they'll have field repairable, even printable components, and that with these practical advantages is going to come with inevitable uncertainty in the systems that our control algorithms are going to have to cope with. And I think that these algorithms are not only going to have an effect on the robots crawling across Phobos, I think they're going to have an effect on our classrooms and research labs where researchers and educators can download robots and assemble them and have them on the very first day running, manipulating, and climbing. Okay, with that I will stop and I will happily take any of your questions.
Questions?
Hey, I want to ask why is the robot always walking in a half-sit position? Does that come from the optimization or is that design?
Yeah, so the question was, why are the robot's knees always bent? So there's a couple reasons for, well, the main reason why that's the case for us is because of the singularities in the kinematics that arise from a straight leg. So we're constantly computing Jacobians for contact points on the feet, and these Jacobians become singular when the leg goes straight. So there's a sort of numerical reason there. Another reason, which is not really the reason we're doing it, but for other robots in the wild that walk with bent knees, is because underlying their control system is the assumption that the center mass height is constant, and that's a lot easier to achieve if you're walking with bent legs. So you can kind of do this and regulate your center mass height. Yes?
Do you think that the fundamental difference between what nature is able to accomplish with walking and what the robots can do is like a hardware issue with sensors and technology, or a software issue with the LQRs?
Yeah. So I think, so the question is the discrepancy between mechanical systems and biological systems, is it largely hardware or software? I think there's elements of both for sure. We can improve in both. But I think for even a very good hardware design, we don't have the algorithmic techniques to do all the things we want the system to do, right? So we don't know how to generate arbitrary aperiodic efficient motions for getting over challenging terrain. We just don't have the algorithms to do it. So although I think progress in both areas is necessary, I think that we have a lot of work to do on the software side. Yes?
Is the physical robot really able to walk in knee-deep mud? Because I couldn't. And when it emerged from such mud, wouldn't it have to be totally wiped off in order to not ruin itself?
Very good. So the question was, can the physical robot actually walk through knee-deep mud? We haven't tried it. I wouldn't say it's impossible. What I would say is it's not good for that robot, right? So hydraulic robots don't like small granules on their actuator shafts and things like that. So they're fine with getting wet to some extent, and they're fine with oil being all over it, evidently, because there's always oil all over the robot. But getting like sediment and things like that could cause problems. So we probably, if we did the experiment, would try to hose it off or something. Yeah. Yes.
There's a lot of focus in your talk on bipedal motion. Yes. Is quadrupedal easier or harder, and why?
So the fundamental problem is the same, I would say. There's additional complexity that arises from having to decide on gait patterns and things like that, which is not really a concern for bipeds. It's really only one way to do it. Modular running and things like that. So I think that at a fundamental level, they're the same, and I'd have no problem working on quadrupeds versus bipeds. They just have slightly different practical applications, I'd say. Yes.
So for systems like Atlas, if you think about in the future, what do you think are the main things that need to be improved to make them more useful, more capable? Is it on the perception side, the control, learning? What are the pieces that? Yeah, so let me tell you. So the perceptions things that we're doing are relatively straightforward. I wouldn't say we're doing anything super advanced. So I think for more general applications, that perception is going to play a major role. I think the control systems are not where we want them to be. We can do some pretty basic things, but walking over really general terrain and like sand that is moving underneath the feet, all these kind of things you might want these robots to do, we still don't have solutions to that yet. And in terms of learning, one of the things that we would really like to explore is doing adaptive control for a system like this. So as I said, we thought very carefully about the model, and we did SysID, and then we froze it.
But inevitably, there's going to be some discrepancy between this model and what the actual robot's doing, and maybe the robot's actually changing slightly over time, and having control systems that can sense that and adapt to it over time is, I think, exactly the right thing to do. Yes?
Since you mentioned prostheses and orthoses, as you bring unpredictable humans into the loop, how can your algorithms be applied, or what would be the main challenges?
Yeah, so that's the big difference, right? So if you have this very complicated dynamical system interacting with the thing you can actually sense and control, that's a whole different ballgame. So, I think that there's some interesting work that's going on into neural implants, right? So you can better sense what's going on with the human through those. You can imagine, sticking IMUs inside people's clothes and, and their wristwatches and things like that, and using that to estimate the state of the person and feed that back into the control algorithm. I think the big thing that the thing that if we could solve would really make a big impact in prosthetics is being able to predict when someone's about to change their gait or when they're about to change the sort of type of terrain they're going on, and try to do a little bit more than just being reactive to that kind of thing. I think that's really where the frontier is there. Yes?
So do you see any relation between this type of much more low-level control to more symbolic high-level control? Because I guess when people want to specify tasks, dragging the robot limbs is a little bit clunky. They want to kind of give a more symbolic representation. It's very high level.
Absolutely. So I guess I didn't talk about that part of the system, because that's not really the part I worked on the most. But we have been thinking about a lot of how do we represent sort of procedural information in a way that's useful, so that although I showed an example where someone's dragging the hand around, that's not the way they prefer to interact with the robot. We prefer to say this is a task where you pick up a drill and cut a wall, and it knows how to sequence a reasonable set of actions. It knows when there's sort of guard functions that detect when that action succeeds, and if it can move on to the next thing, or if it has to ask for the human for help. So I think that really making these systems have very low levels, very sparse human interaction, you absolutely need like the temporal logic type specifications operating at a higher level. And that's really, I think that's going to make or break the practical applications of systems like this. Whether you need an expert operator to fly in with the robot, or you can just fly the robot to a worker who roughly knows the environment that they want the robot to work in. Yeah.
You showed two robots, a U-robot and the Atlas.
Yeah.
Whereas Atlas, most of the approaches were model-based, and the U-robot, it was most reinforcement learning-based.
Yes.
Did you try other approaches in the other robots, and how did it work in that?
Yeah, so there's nothing innately specific about the robots that would require one approach over the other. Basically, you can think of it as exploring an algorithmic technique and applying it to the U-bot. I think there's plenty of room to do model-based control on the U-bot. I think it has some nice properties. There are things that make it a little bit hard, like backlash in the wheels and the wheel slipping on the ground during these aggressive maneuvers and things like that. But you could certainly go pretty far with model-based control. In fact, the balancing controller for the wheels is just using LQR. Yes, Semo?
So with these very aggressive movements like running and whatnot and jumping, I'm guessing you're not going to try this on the real robot, right?
So
my real question is, what does it have to happen in terms of robustness guarantees or theory to ensure your advisor that it's safe to run?
Yes. So the question is, to what extent do we require guarantees of the performance of controllers to do very aggressive things on hardware? So I think the answer to that is we're not able to make robustness guarantees about a system like Atlas. I think with the level of parameter uncertainty in the model and the dimensionality of the system, that if we tried to do like sauce verification, we'd have a really tiny funnel if we were able to compute it at all, right? So I think we're not doing that. And I think we're not scared to try very aggressive things, particularly after competition deadlines, right? Or right before when the robot's going to get upgraded, it's no problem to do these things, right? So I think if you're not breaking your robot all the time, you're not doing good robotics. At least good control-based robotics. So yeah.
All right, thanks again.
All right, thanks.